Hey everyone, welcome to the first episode of Everyday Physics. Today is our pilot episode, so we're going to be talking about flying. We're going to look at projectiles with a baseball. We'll slow that down a little bit so you can look at it closer. I throw it as flat as possible and it lands. We take some measurements. Let's do some math. We measured that I threw the ball from about a height of 2 meters and it traveled horizontally a distance of 7.7 meters. Now the next thing we need to think about is the fact that the vertical and horizontal components of the velocity are separate from each other. Now we can make graphs of each. The only force acting on the ball as it's moving is gravity, and gravity only affects the vertical component of the velocity. Vertically, it starts with a velocity of 0, since I throw it horizontally to start. And then it accelerates downwards the entire time until it finally hits the ground. I think of downwards as negative. The horizontal component of the velocity starts with the initial velocity that I threw it at and stays the same all the way until it lands on the ground. There's two key things to notice from this graph of vertical velocity versus time. First of all, when objects fall in free fall towards the ground, they fall at an acceleration of negative 9.8 meters per second squared. Acceleration is just the change in velocity over time, in this case the change in vertical velocity over time, or the slope of this graph. The second thing to notice is that the area under this graph is going to give us the vertical displacement, or the total distance that it falls vertically. We can find the area under this curve in terms of t. We know that this side is t, and since the slope is 9.8, this side of the triangle, we're looking up at this graph, this side of the triangle is going to be 9.8 t, so when you find the area of that triangle, it's going to be 4.9 t squared. We know what our vertical displacement is. We measured it at the beginning. It's 2 meters. So we can set this 2 meters equal to the area under the curve, 4.9 t squared, and find out that the time it was in the air is 0.64 seconds. The other thing that we want to figure out is how fast I initially threw it. It only starts with a horizontal velocity, since I throw it horizontally, and this can be given as the total distance it traveled horizontally over the time it's in the air. That's easy. It's just 7.7 meters that we measured at the beginning over the 0.64 seconds we just figured out, and I threw the ball at about 12 meters per second. One more cool thing that we can figure out is its final velocity when it hits the ground. So the ball starts with both gravitational potential energy and kinetic energy from me throwing it. It finishes with only kinetic energy. The gravitational energy at the beginning is converted into kinetic energy. So the other convenient thing about this equation is that I don't know the mass of the baseball, and I don't need to. The mass is in all three of these, so I can cancel it out. Next, we can just plug in the numbers that we know. G is 9.8 newtons per meter. Delta Y is 2 meters. The initial velocity is 12 meters per second. So if we do this in a calculator, we can find out that when the ball lands, it's traveling at 13.5 meters per second. Well, you may be thinking to yourself, that's all great, but what if I want to throw it with an initial launch angle? That's no problem. So we know we're starting with a launch angle of 30 degrees, it's thrown from a height of 2 meters, travels a horizontal distance of 7.4 meters, and it's in the air for 1.06 seconds. We want to find what speed it was thrown at, what speed it lands at, and its max height in the projectile. So what we're starting with is a little bit different here. This time we know the time, last time we didn't know the time, but the fundamentals of how you solve these problems don't change. I always like to start with a picture of the situation. So we got our 2 meters, 7.4. We know at some point it hits a maximum height. It's launched at 30 degrees. So the first thing that we need to do is figure out the components of the velocity. So since this velocity has an angle to it, we can split it into the horizontal component and the vertical component using vector addition. And now we get to use some trig. The horizontal component is going to be the initial velocity times the cosine of the launch angle, and the vertical velocity initially, it does change, is the initial velocity times the sine of the launch angle. The cosine always gives the horizontal component, the sine always gives the vertical component. Now that we've got that all figured out, we can draw some graphs of the situation. Once again, we draw vertical and horizontal velocity separately because they're independent of each other, with the only common thing being time. The main difference on this is that rather than our initial vertical velocity being 0, it starts with an upward initial vertical velocity, which I marked here. So this whole time, it's going up at a decreasing speed. That's this part of the projectile. At some point, the vertical velocity is going to be 0. That's when it's changing from going up to going down. And all of this after, it's going to be going down. That's this part of the projectile. More on that later. Now that we have our graphs drawn, I think the easiest thing to solve for first is the horizontal component of the velocity. The horizontal component of the velocity remains constant the entire time and can be given by the change in horizontal distance over the time it's in the air. We know both those things. It travels 7.4 meters in 1.06 seconds, 7 meters per second. That's this number. If you wanted to find that graphically, you could just realize that this is a rectangle. The area under the curve has to be 7.4 meters that it traveled, delta x. You could just divide by the 1.06 seconds and get to that same answer. Now that we know the horizontal velocity, we also know that that component of the velocity is equal to the total initial velocity times the cosine of the launch angle. So we have 7 meters per second equals v0 times cosine of 30 degrees, or v0 equals 8.1 meters per second. All right, now that we know what v0 is, we can find what the initial vertical velocity is in order to find the max height of the ball. So the initial vertical component of the velocity is just v0 times the sine of theta, or 8.1 meters per second times sine of 30, or about 4 meters per second. Now we can look back at our original graph of vertical velocity versus time. We plug in this 4 meters per second as the initial vertical velocity. And now if we look at this graph, this entire time from here until it hits 0, the ball is moving upwards at a decreasing rate. For this instant where the vertical velocity is 0 is where it's going to hit its max height. So it'll be going up, up, up. It'll hit that point. It'll temporarily be at rest, vertically speaking, and then it'll start going down until it reaches time t equals 1.06 seconds where it hits the ground. We can write a simple linear equation for this line. The vertical intercept is 4 meters per second, and the slope, as we determined earlier, is g, or 9.8, negative in this case, since we're thinking of upwards as positive. So it's going to be negative 9.8 t. If we set this equation equal to 0, we can find out where this max occurs. And we find that it's t equals 0.41 seconds. Next, we could take this and find out what height that actually is by using the area under this graph. The area under this part of the graph is going to give us how much it goes up before it starts going down. We know that this side of the graph is 4 meters per second, and this side is 0.41 seconds, so we just found that. So our maximum y point is going to be our initial 2 meters plus all of the distance that it goes up, which is the area under this graph. It's a triangle. It's 1/2 times 4 times 0.41. And we find that our max height is 2.8 meters off the ground. All right, the last thing that we wanted to figure out here was the final velocity when it lands. So before we had to think about components and how high did it go in the air and all that stuff, this is just a simple energy problem. We don't need to worry about that anymore for this. The ball starts with kinetic energy from throwing it at an initial velocity v0, and it has gravitational potential energy since it starts at an initial height above the ground. It finishes with just kinetic energy. So now, since the mass is in all three of them, we can cancel it out, which is nice. I didn't take the mass of the baseball, and I don't need to. Now we can just plug and chug the numbers that we know, do some manipulation, take a square root, and find out that the final velocity of the ball is 10.2 meters per second. Thanks for watching. Hopefully you enjoyed this video. Hopefully you learned something new or clarified something you didn't fully understand before. As you can see, this is a pretty simple lab. All you need is a baseball and a measuring tape, and you can do this at home yourself. So, see you later.